right? In a product is at most the length of product of the length of the vectors. Good. So what this says, put together this and this. What this says is that xj times bj tilde squared is at most the length of bx times bj tilde. In other words, the length of bx is at least bj tilde times the absolute value of x sub j, but x sub j is an integer, So this is at least the length of bj tilde. Okay, and yes, so in particular, the length of bx is at least the minimum of the length of the Gram-Schmidt vectors. Okay, so we saw that given this fact, any LLL reduced basis contains a very short vector. The first vector of an LLL reduced basis is an exponential approximation to the shortest vector. Okay, so it's a complicated analysis, but the point is that this whole exercise reduced the problem of finding an approximately short vector, exponential approximation to the shortest vector, to computing an LLL reduced basis, a basis which satisfies these two properties. Okay, so that's the next step. Okay, okay, so I'm gonna erase this. So let's move on to step 2, the LLM algorithm. Step 2. So what is this algorithm, right? It's an algorithm that takes as input a basis B and outputs a basis LLL delta LLL basis B prime. Okay, so this is what we want to do. So let's let me describe this algorithm, but on the side, let's also work out an example, right? So how does this algorithm perform on one of these spaces that that we have? Okay, so in fact, I will keep using my favorite lattice, 2, 0, 4, 0, and 1, 1. Okay, so I'm going to start with the basis B1 here and B2, which is this relatively long basis vector. Okay, so this is the basis that I start with, and I want to reduce it to something smaller. So how do I do this? The first thing I do is compute the Gram-Schmidt orthogonalization B1 tilde up to Bm tilde. Okay, I have a basis, compute the GSO. There are two main steps to the LLM algorithm. The first is called the reduction step. Intuitively, the reduction step makes sure that the first property of the LL reduced basis is true. And then we'll have a swap step which makes sure that the second property of the basis is true. Okay, so what does a reduction step do? It is essentially, so if I iterated sort of a loop which works as follows. This is very important. Bj where Crj is nothing but Bi in a product with Bj tilde, Bj tilde, Bj tilde. Okay, so let's look at it a bit closely. What it does is it takes every vector from the second vector onto the nth vector, because the first vector, the Gram-Schmidt orthogonalization is the same as itself, so forget it. Go from 2 to n. And for each of these vectors, let's look at all the vectors below it, right? For all vectors I minus 1 down to 1. And I'm going to iteratively subtract multiples of Bj from Bi. Okay, so that's what it does. Where this multiple is computed in this weird way. So let's forget about it for a minute. Let's go to the picture and see what happens. Okay. So I have B1 and B2. Okay. The Gram-Schmidt orthogonalization of B2 is this B2 tilde. Okay. How did I get from B2 to B2 tilde? Right. How do I go from B2 to B2 tilde? I take B2 and I subtract a multiple of B1. Right. What multiple of B1 do I subtract? It turns out that this is B2 tilde in this picture is B2 minus 3/2 B1. Okay, because I shifted it by B1 and then half of B1. Okay, so in other words, the Gram-Schmidt for this basis B1 and B2, the Gram-Schmidt coefficient mu sub 2 comma 1 is 3/2. Okay, so that's the way it was defined, right? So it's the multiple of B1 that I subtract from B2. Now that's very bad for us because I want a basis where this mu ij is smaller than half, right? I mean, this is clearly not true. Now, the question is, how do I make sure that it is in fact smaller than a half? I take B2 and I shift it by multiples of B1, right? I take B2 here and I subtract, a single multiple of B1. I get this guy. Now, for this new B2 prime, the Gram-Schmidt orthogonalization, which actually remains the same, right? Because even though I changed B2 to B2 tilde, the orthogonalized vector remains the same. This guy is now B2 minus a half times B1 prime. Okay, so now B1 prime, no, B2 prime minus B1. Now B1 together with B2 prime satisfies the first condition of the LL reduced basis. Okay, and that is in fact what happens here. I mean, it's complicated, but it looks complicated, but it isn't. This is exactly what happens here. You take each vector, 2 to n, and you shift it by an appropriate multiple of Bj. What is appropriate? It is essentially, this is actually the Gram-Schmidt coefficient rounded to the nearest integer. Okay, so when I do this operation, what I'm doing is I'm taking two lattice vectors and I'm subtracting an integer multiple of one from the other. So, the new vector is in fact another lattice vector. So I don't go out of the lattice. I always have a lattice vector. Okay, so that's what the reduction step does. And so this is the geometric picture. let's sort of look at the algebraic picture. So what happens algebraically? So again, let us write down B1 up to Bm as B1 tilde over the length of B1 tilde. So this is the orthonormal basis times 1 mu 2 1 mu 3 1 etc. 1 mu 3 2 and so forth, right? And it is this matrix that we are interested in. So what are we doing in the reduction step? Let's fix an I, right? So let's say I equals 3, right? So that is the second iteration of the outer loop. Okay, I equals 3 iteration of the outer loop. What we are going to do is we are going to look at each of the columns to the left of the ith column. So j equals I minus 1 down to 1. And we are going to, so let's call this, okay, there's a 1 here. Okay. So I'm going to take this mu 3 2 and I'm going to subtract a multiple of the second column to make sure that mu 3 2 is at most half. Okay, so let's say this guy is actually 3.5 to begin with. I will subtract 3 times the second column, which will bring it down to 0.5. Okay, so this is an operation that I do on this matrix. This is sort of an elementary column operation that I do on this matrix, right? What the effect on the basis is that I take the second basis and I take B3 and I change B3 to B3 minus 3 times B2. Okay, that's what happens when I do this operation. Okay, so that makes sure that this guy is smaller than a half. Let me do, so now I'm going to subtract a multiple of the first column from this guy. So let's say this guy is 4.5 to begin with. I'll subtract 4 times the first column, which will bring it down to 0.5. That's great. And now comes the interesting part. Okay, when I do this, when I subtract a multiple of the first column from this, it doesn't change the value of this number, because what I have here is 0, right? So what this says is that if you take LLL and change it just a tiny bit, namely, you don't go down from I minus 1 to 1, you actually go up from 1 to I minus 1, the algorithm is wrong. It just doesn't work. Right? Why is that the case? Because so let's say I take this guy, I subtract the first column, which makes sure that this guy is smaller than a half, right? And then I take this guy and subtract a multiple of the second column. That makes sure that this guy is smaller than a half, but now this guy got messed up because I subtracted some unknown multiple of mu 2 1 from this, right? So who knows what happens? So very important to do this from I minus 1 to 1. But in any case, the effect is that this matrix, all these coefficients, so the off-diagonal coefficients, become smaller than a half. So that's what happens in the first step, in the reduction step. Okay? So far, we didn't say anything about the second condition, and that is taken care of in the swap step, and it's in fact almost trivial. So what this says is, if there exists an I such that delta minus mu I plus 1I squared I tilde squared is bigger than I plus 1 tilde squared, then swap Bi and Bi plus 1 and go to step 1. Okay, so let's look at this a bit more closely. Okay, so what this says is that if the second condition of the LLL reduced basis is not true, so the second condition says that bi plus 1 tilde squared is smaller than, it's at most this quantity. So this condition says if it's not true, then you swap bi and bi plus 1. Okay, you're not done yet because the second condition is not satisfied. So you swap bi and bi plus 1 and you go back to the first step. Repeat it. Do the same thing. You have a new basis, so you need to compute a new Gram-Schmidt orthogonalization. Do this again. Okay? Keep repeating it, doing it again and again until you hopefully terminate. Okay, this is the algorithm. Does it terminate or not? We will see that it does. Okay? But before going there, let's make sure that after this algorithm, if this algorithm does terminate at some point, the output basis is a delta LLL reduced basis. Okay? Let's make sure that that's the case. Why is that the case? Because after the reduction step, the basis satisfies the first condition of the LLL reduced, delta LLL reduced, and either this step goes back to step 1 or it terminates. And if it does terminate, then for every I, bi plus 1 tilde is at least this quantity, which means that the second step is satisfied. Okay? So if it does terminate, look at the last iteration. The basis that it outputs is a delta LLL reduced basis. Okay? So correctness, it's very easy to see. Okay? The question here is, does the algorithm ever terminate or not? Right? Because it could be that this condition is never satisfied and you keep going on and on and on. Right? So that's the main sort of question. With this algorithm, we want to prove that it's not just doesn't just terminate; it actually terminates in a polynomial time. Yes.
Are you just swapping the smallest I? That's it.
Yes. So if there exists, so any I, in fact. So either for every I this condition is satisfied, or there exists some I. Maybe there are like 3 or 4 I's, right? Pick an arbitrary such I.
You just swap one.
One. Exactly. Okay. So there is a priori there is absolutely no reason to believe that this algorithm terminates, right? But it does. That's actually the magic. Okay. So I'm not going to show this formally that this algorithm computes an LLL reduced basis, but we saw that that's in fact true, right? So first step takes care of the first property, the reduction step takes care of the first property, and the swap step takes care of the second property. Okay, this all works nice. Okay, so the last thing to show in 6 minutes, it's a challenge, is that this algorithm terminates. Okay. Good. So so this goes in really 2 steps, right? So one, I'm going to bound the number of iterations, and this will be sort of polynomial in the input length. We'll see what the input length is in a minute. And 2, bound the running time of a single iteration. So the second step is actually it's more or less easy, right? Why is that the case? In a single iteration, I only do a polynomial number of arithmetic computations, right? So in fact, n squared, subtractions and a bunch of divisions and a bunch of comparisons. So clearly a polynomial number of arithmetic operations. But the problem is that the numbers involved in this computation can actually become large. Right? So assume that you have a number x and you do sort of n repeated squarings. Okay, the resulting number becomes x to the 2 to the n, which has 2 to the n bits. Okay, so even though you did only a polynomial number of steps, the number became so large that in fact the running time is not polynomial. Okay, so this kind of thing could potentially happen here. Anytime you deal with a numerical algorithm, this kind of thing could happen, and you have to prove that that's not the case. Trust me on this. This can actually be done. It's a bit messy, but this can actually be done. The interesting part is step 1. To prove that the number of iterations before which this procedure terminates is polynomial in the input line. Okay, so that's what, so this, trust me, and this we will show. The proof is actually very, okay, so let me, before I go there, let me say what the input length is, right? So what is the input length? What is the input? It's a basis, right? You have m vectors. The input length is at least max of, okay, so I have m vectors. To represent each vector, I need at least one bit, right? So it's the max of m, and to represent a certain vector, a length vector bi, I need, I claim that I need log the length of bi bits. It's not, I'm assuming integer vectors actually. So I'm assuming that my initial basis is all integers, you know, and therefore, you know, all the intermediate bases are also integers. Now the thing is, yeah.
Choose the entries of the vectors like real number.
If you choose them to be rationals, it's easy to take care of, right? Because rational basis, you just multiply everything by the least common multiple of the denominators, you're done. Real numbers, you know, how do I even represent the real numbers in a computer, right? I mean, I have to sort of cut it down at a certain level of precision, and then it becomes really rational. Say that again. I can still. I mean, if you have space to store a real number, yes, you can run LLM. You're right. Say that again. Error term. Yeah. So that's what I said. If you take the real number and cut it down to certain levels of precision, you will have an error term, but it's not obvious how this error term multiplies when you. So there are questions about the numerical stability of this algorithm. So if you run it with sort of real numbers, you cut down to a certain amount of precision, you know, do you get an approximation to the shortest vector in the original line? I mean, there are all these issues, which is why I wanted to, you know, circumvent these issues and talk about integer basis. So there are issues which I don't want to get into. It's a good point. Okay. Okay, so so when I say polynomial in the input length, I have to say what the input length is, right? So I claim that the input length is really max of m, the dimension, and the log of log v1 up to log v. Okay, so why is this the case? Because if I have a vector b1, right, of length b1, the number of bits that I need to represent, I mean, how do you compute the number of bits that you need to represent this vector, right? So the number of vectors of the same, of this length, so let's say you have the length of b1, you have a sphere of surrounding the origin with this radius. the number of vectors in this sphere is of the order of 2 to the length of V1. Right. Sorry. Of course not. So this is O of V1 to V over n factorial or whatever, it doesn't matter. But certainly the number of vectors in the sphere of this radius surrounding the origin is V1 to VR, right? It grows exponentially in the dimension, and therefore the number of bits that I need to represent, write down V1 is a log of this number. Log of V1 to Vm is m times log. Okay, so in any case, the point is, what I want to do is I want to compute probably a very loose lower bound on the input length, just so I can talk meaningfully about a polynomial in the input length. Okay, so forget about, this is parentheses, keep it in your head. The main claim is that the number of iterations is polynomial in M and log of the max of the BIs. Okay? And I claim that this is really the input length. This is really polynomial in the input length. Okay? So why is this true? The analysis how do you bound the number of iterations? Okay, so whatever this number is, we'll come to it later. The analysis uses a classical technique in analyzing algorithms, namely the potential function method. Okay, so you have a basis, you're going to convert it to another basis, and you're going to keep doing it in different iterations. What I'm going to do is I'm going to associate a number with each basis. Okay, I'll call this the potential function. And I will show that the original potential function, when you start it off, is not too high. So it's bounded, but not, it's exponentially large, but not too high. And in every iteration, the potential decreases by a constant factor. Okay? So that will give me a bound, and the final potential is at least 1. That will give me a bound on the number of iterations. Okay? So that's the idea of the proof. So really, the main question is, what is the potential function, right? So phi of B, define phi of B to be the product of B1 tilde, B2 tilde, up to Bi tilde. I equals 1 to M. Okay, so this is a bit of a strange expression. Why is that the case? Because for I equals 1, I'm going to count B1 tilde. For I equals 2, I'm going to multiply it with B1 tilde times B2 tilde. And B2 tilde, B2 tilde. So B1 tilde gets counted many times. So this is in fact equal to the product of B1 tilde, Bi tilde to the power M minus I plus 1, perhaps. M minus I plus 1. Okay, but this is what I want you to focus on. Okay, so what is this number? The product of B1 tilde up to Bi tilde. What is this number? Okay, consider the lattice generated by B1 up to Bi. Okay, so this is a sublattice of the original lattice, and its Gram-Schmidt orthogonalization is in fact B1 tilde up to Bi tilde. Okay, and the product of these guys is in fact the determinant of the sublattice. Okay, so this is the product of I equals 1 to M. Let me call it D sub B comma I. Let me call this number actually B, but D sub B, which is a product of the determinant of lambda of L generated by B1 up to Bi. Okay? So many sublattices, M sublattices, take the product of the determinants, that's this number. Okay? So this is the potential function. So what is the initial potential function? So the initial value of dB. So what is this number? Well, each Bi tilde is at most, the length of Bi tilde is at most the length of Bi. Right? So this is at most max the length of Bi's to the power m times m minus 1 over 2. Okay? Because I'm counting each Bi multiple times. If I upper bound this using the maximum length of all the Bi tildes, this is what I get. I'm going to sum up, m minus I plus 1 over all I. This is what I get. Okay? This is a very, very loose upper bound. That's all I need. The point is to note that the log of this number, which is m times m minus 1 over 2 times log of the max of the length of Bi, is in fact polynomial in the input length. Okay? The input length is this. The log of the original potential is polynomial in the input length. So that's the initial value. What I want to show now is that this guy decreases very fast. Okay. So why does it decrease? Well, when I do the reduction step, okay, I change the basis quite a lot. But the key thing to observe is that I don't change the Gram-Schmidt orthogonalization. Okay, and why is that the case? Well, it's best to see this by example, right? Let's say I have this basis for the same lattice that we talked about before. What I do, the kind of thing that I do in the reduction step is I take B2 and I shift it. So this is the original Gram-Schmidt orthogonalization. What I do in the reduction step is I take B2 and I shift it by an integer multiple of B1. Right? So the B2 goes from here to here, but its Gram-Schmidt orthogonalization remains exactly the same. Okay, so in fact you can show that the first step doesn't change the GSOs at all. So that's that. The second step, it takes two vectors, some two vectors I and I plus 1, and swaps the two vectors. Okay, that changes. The order of the vectors matters a lot for the Gram-Schmidt orthogonalization. So this changes the GSOs. Now let's see how this changes the potential function. Okay, so we are interested in dB prime divided. Let's see. Okay, so let's denote this by, this is B is the initial basis, and B prime is the final basis. B prime is the basis when you started off the swap step. B is the basis you started off the swap step, and B prime is the basis that you ended up after you swapped the two vectors. Okay, so B is the product of dB is the product of dBi, which are numbers of this form. Have dB prime, which is the product of dB comma I prime, which is these numbers computed for the resulting basis for the B prime that came out of the swap step. Okay. Now what I want to compute is dB divided by dB prime. Okay, so what is this? Observe that if I look at the vectors 1, 2, 3, 4 up to I minus 1, they remain the same before and after because I didn't change them at all. I just swapped I and I plus 1. Right? So the dB, so dB1 is equal to dB prime 1 up to dB I minus 1. Okay? This doesn't change at all. The ith guy, it changes because there was the ith vector here, and when I swapped it, it became the I plus 1th vector. But how about the other vectors, dBi plus 1? So this is the determinant of the sublattice generated by B1 up to bi plus 1. D prime bi plus 1 is the determinant of the sublattice generated by B1 up to bi minus 1, bi plus 1, bi. Okay, so the set of vectors is exactly the same, therefore the determinant is the same as well. So these are all the same. The only thing that's different is the ith step. Okay, so this is the determinant of the lattice generated by B1 up to bi minus 1 and bi plus 1 prime divided by db divided by the determinant of the lattice generated by B1 up to bi minus 1 bi. Okay, so this is the only difference between the two steps, between the two determinants. So what is this guy? So this guy is really B1 tilde, product up to bi minus 1 tilde. Okay, so this is all the orthogonalizations for 1 up to I minus 1 vectors. And now I have to orthogonalize bi plus 1 relative to B1 up to bi minus 1. Okay, so when I do that, the only things that survive are the bi plus 1 component and the bi component. Okay, because when I compute, I write bi plus 1 as a linear combination of b1 up to bi minus 1 plus a couple of vectors sticking out. Okay, what are these vectors that are sticking out? bi plus 1 tilde and bi tilde, some linear combination of bi tilde. Right, so this is exactly the vector that survives, divided by b1 tilde up to bi tilde. Okay, this is the original basis, nothing changes, and that's what it is. So this is, lo and behold, all these things cancel out. What you're left with is the length of bi plus 1 tilde plus mu I plus 1i bi tilde divided by bi tilde. Actually, yes. Okay, so that's what is left. And what this condition says, what the second condition in the definition of LL reduced basis says, is that this is at most square root of delta. Okay, so we need to rewrite this a tiny bit. Right, so what this says is that bi plus 1 tilde plus, I'm going to take this aside, plus mu I plus 1 I bi tilde, the length is at least delta times the length of bi tilde squared, of course. Okay, so the ratio between these two,
We're looking at the case where that's not satisfied.
well, that's not satisfied. Exactly. So that's why this is smaller than square root delta. Okay, what is square root delta? You know, set delta to be 3/4, so this is like root 3 over 2, which is smaller than 1. So what this says is that dB prime is smaller than dB. Okay, so the potential function decreases with every iteration.
Could you explain again why
Yes.
it is less than square root delta?
Good. So the second condition, it says that the ratio between, so this is just a rewriting of the second condition. I just took this term to the left hand side, right? This is just a way of rewriting it. Now, divided by bi tilde, right? So there's a square here, right? So when I divide it and I take the square root, I get the square root of delta here. So this will be the case if the basis is LL reduced. Okay. Now we are looking at it as pointed out here. We are looking at an iteration where the condition here is not satisfied, and that's why so if it is satisfied, we terminate. If it's not satisfied, then
not satisfied for this specific I.
For
This I.
for this specific I. Yes. So in fact, we saw that the ratio between the potential functions of the two bases depends only on this specific I, right? Because this is the only I that I spot. And for this specific, that's the condition that I check, right? So for this specific I, the ratio is smaller than square root of delta. So, okay, good. So what this says is that the original potential function is some number of this form. It decreases by a factor of square root delta every time. So that gives us a bound on the number of iterations. Okay. So what this says is square root delta to the number of iterations, call it t, times the original value, which is max pi over I, to the m times m minus 1 over 2, is so at the end of all these iterations, the potential function has to be at least 1, right? Because it's a product of determinants, and the determinant of each sublattice is at least 1, and therefore the product is 1. And this gives us a bound on t, which is t is at most m times m minus 1 over 2 log max bi divided by log 1 over root delta, I think. Yes.
So your proof says that M,
Yes.
dimension of the lattice,
Yes.
is not necessarily equal to the dimension of the irregular space. So it's because we didn't define the volume of the lattice.
Uh-huh.
The volume of the two-dimensional lattice in n-dimensional space.
Good. Exactly. So one has to. So I defined m-dimensional lattices which are generated by m vectors. Right? I didn't define. One can define lattices that live in m dimensions that are generated by less than m vectors. In fact, you can define determinants and so forth. So, in fact, I'm not even going to. The only characterization of the determinant that I'm going to use is that it's a product of the Gram-Schmidt orthogonalizations.
So you define the dimension of the sublattice
Yes.
in the proof of the potential function.
Yes.
Dimension of the sublattice and the volume of the sublattice.
Yes. So the volume of the parallelepiped of the sublattice. So the sublattice lives in n dimensions,
Yeah.
but it only. So think of this lattice, right? This lattice in 2 dimensions. So it lives in 2 dimensions, but it has rank 1. Okay, so one can define sort of volumes and can define parallelepipeds and determinants and so forth for such lattices as well. The only thing that I'm using here is that the determinant of such a lattice is the product of the Gram-Schmidt orthogonalizations. That's the only thing I'm using.
I don't think you're using that. I think you can just write everything in terms of product to them.
Product of 2 guys?
Product of di tildes. I don't think you're using that. And you can follow everything written with product of di tilde forms.
Yes. Good. Excellent. So I don't. So this going to the talking about the determinants was just for intuition. I mean, so you can do all this computation by just talking about the product of the Gram-Schmidt orthogonalizations. You don't need to even go to the determinant, but you can if you want. That's there. Okay. So together, all this effort shows that there is an algorithm that gives you roughly a 2 to the m approximation, 2 to the m over 2 approximation of the shortest vector. Okay, so I'm vastly out of time here, 20 minutes out of time. But let me just mention a couple of applications of LLM. Right? The first application is to find. So this only gives you an approximate shortest vector, right? The first application is to find an exact shortest vector in certain lattices. Okay? So assume that you have a lattice with a very short vector, and the second shortest vector is an exponential amount times the length of the first shortest vector. Okay? So assume that you have a lattice of this form. So this is the first basis vector, this is the second basis. This is lambda. This is lambda 1, and this is lambda 2. Okay? So now if you run LLL on this, any basis of this lattice, you're going to get a vector that is 2 to the m. So this is, let's say this is at least bigger than 2 to the m minus 1 over 2 times lambda 1 of L. Okay? You're going to get a vector that is at most 2 to the m minus 1 over 2 times lambda 1 of L. In other words, you're going to get a multiple of the shortest vector. Okay? Because the second shortest vector is really hugely long, so it cannot be, the output of the LLL algorithm cannot be the second shortest vector. So it's a multiple of the first shortest vector, and in fact you can compute the really shortest vector by dividing it by an integer multiple. Okay, so for lattices, for these special lattices which have a short vector and the second shortest vector is really huge, you can actually compute the exact shortest vector.
So I'm not sure what that means. I mean, polynomial time means in that case.
Well, look at it. The length of this vector. So the length of this vector is exponential times the length of the shortest vector. The number of bits that you need to represent it is only log of this number. Okay, so it's log of this number, which is m plus log of. So that's still polynomial. So that's one thing. The other thing is what's called Coppersmith's method, which I won't have time to talk about at all. And what it does is the following. Let me just describe it very quickly. Okay. So consider it's used to break RSA if a number of bits of the inverse are known. Okay, so in other words, let's say you have m equals x, c equals m cubed mod n, where n is p times q, and I know 1/3 of the bits of n. Okay, how do you know this? Well, you could know this by various side channel attacks, by various other mechanisms. Okay, so assume for some reason that you know small number of bits of n, you can actually figure out the entire n. So this can find the entire n. Okay, so this is the kind of I'm not going to tell you how to do this at all, but this is the kind of application that that you can use LLL for. Okay, you can translate this problem to finding small roots of polynomial equations. You can write this down as a polynomial equation, mod n, and you can translate this problem to finding small roots of this polynomial equation, which you can then transform into a lattice and translate that to finding an approximately short vector of a lattice. Okay, so you can do all this, and this is the kind of application that LLL is used for. Okay, so vastly out of time. My apologies. That's that.